In previous videos, we talked about the geometrical aspect of the aspects of the crystalline lens. We talk about the radii of curvatures. We talk about the thickness. Right now, in this video, we want to talk about the lens refractive index distribution. So first, we need to think about it why we said lens refractive index distribution, not just lens refractive index. Because the refractive index of the lens, the crystalline lens in our eye, is not a constant number. We have a distribution of the refractive index. Or in another word, we can say we have gradient of the refractive index. So let's take a look at the map of the refractive index. As you can see here, the refractive index on a lens is not constant. And at the center, that we call it nucleus, we have the highest refractive index. And when we go to the edge, the refractive index go lower and lower. So the nucleus is the part of our eye, is a part of our crystalline lens that you have it when you're born. But the rest of it, which we call it cortex, is some part that, when you grow, that part adds to the actually crystalline lens. And as I mentioned, the refractive index is not constant. So you can see for 25 years, 35 years, and 45 years old, roughly at the center, which we call it nucleus, we have a constant refractive index. But, the shape and the refractive index change is not constant during our lifetime. So, in another word, the refractive, when we plot it like, that grayscale, that the color is representative of the refractive index, lens nucleus at this part of our crystalline lens, the refractive index is constant. And then at lens cortex, the refractive index from high point goes to a lower point. And, at capsule, as I mentioned before, it's a kind of dead cell that, doesn't contribute that much to the refraction of light, but it keeps the shape of the crystalline lens in a good form that during accommodation, it remains its shapes. So the variation of the refractive, we need a mathematical model for variation of the refractive index. One of a good mathematical model is introduced by Gaussian in 1909. That model, we have a refractive index of y and z. We have a constant number, which is 1.406. And, for each power, we have a coefficient, z minus z0 to the power of 2, z minus z3 to the power of 3. And then, for we have another coefficient, which is y to the power of different numbers, and we don't have any y to the number of to the power of any like 1, 3, 5, because the refractive index of the eye should have a symmetry in y direction. So if you have any odd number of the power of y, then it's not going to be symmetric, because the top part of the lens should be exactly the same as the bottom part. So we only have power of like 2, 4, 6. And in this equation, Z0 is roughly half of the lens. So it's 1.7, and the total thickness of the lens, we consider 3.6 based on this model, which are very well-known numbers, and people usually, when they want to import those models to Zemax, they use these models. And I have another video that I explained based on this mathematical model, how we can actually model it in Zemax using gradient index lens. So you should take a look at that video to see how we can use those coefficients to put it into Zemax. But that's a mathematical equation for the refractive index of the lens as a function of y and z. That y, when let's say our lens is like this, y is in this direction, z is the optical axis, as always. So we have another equation for the refractive index. This equation is just for when you move on optical axis. N naught plus ns minus n naught r to the power of 2p. So n naught is the highest refractive index on optical axis, which should be at the center. because as I said, the refractive index is high, and then when you go to the edge, the refractive index decreases. NS is the refractive index on the lens surface, and P determines the steepness of the gradient. So let's say when you have a high P actually coefficient or number, then the refractive index goes down very fast. So this is a representative of the rate of change in refractive index. In this graph, you can see it better. Let's say, from the center, go to the edge is relative distance from the lens center, and the refractive index, when P is equal to 1, it goes very smoothly. But when P is equal to 2, at the center, as I said, the refractive index is constant. But then when you go to the edge, it goes very fast, goes down very fast. So the steepness, right now we have a little bit lower steepness. Here we have high, here we have super high steepness. So at P equal to 3, goes constant, and then goes to a lower value very sharply. And it's 1.37, the refractive index. So P number is a kind of representative of how much the refractive index changing versus distance. That's another way to actually explain this number. So for the measurement of the refractive index of the lens, we have a lot of methods. One of them, actually all those methods are the method that you cannot do it in live situation. So you extract the crystalline lens and then you measure it. One way is Abbey refractometer, which is a pretty simple device. You have two prisms, and based on the angle you can actually measure based on the Snell's law and angle you can actually measure the refractive index. We can use Talbot, X-ray imaging, fiber optics refractometry. And in vivo measurement, one of the methods that usually use is first use MRI. That MRI, I think, stands for magnetic resonance imaging. So based on that image, you can map a spin to spin relaxation time on our eye or any part of our body. So you can have a map of that spin to spin relaxation time, and based on that we can have a map on protein concentration on our crystalline lens, and from that protein concentration we can actually find the refractive index distribution in our eye. So based on this method we can actually measure the refractive index of the eye. So here are references that I use for this video. Thank you very much.